So, last class we have discussed about the 8086 architecture. Now, we will discuss about the different pins and the functions of the different pins. Of course, we have discussed most of the functions already while discussing about the architecture and the microprocessor operations. So, coming for this 8086 is a 40 pin IC available in dual inline package. This is a 40 pin IC. Available in dual inline package. Dual inline package means half of the pins will be on one side, half of the pins will be on the other side. So, out of these 40 pins, so in fact it is actually 48 because these 8 pins they are exclusively for minimum mode or maximum mode. At a particular time we can use either these 8 pins or these 8 pins only. So, there are some common signals or common pins and signals. There are some common signals. There are 32 total and 8 exclusively for minimum mode, and 8 exclusively for maximum mode. As I have discussed yesterday, in minimum mode it is a single user this configuration, whereas maximum mode is multi user. So, first I will discuss about the common pins. So, if we come for this common pins, so we require VCC and ground for any IC. So, we have one VCC which is equal to 5 volts, and one specialty of this 8086 is this is having 2 grounds. So, the reason for having the 2 grounds is to cancel the noise. So, the remaining are, we know that microprocessor 8086 having 20 address lines and 16 data lines. The lower order 16 address lines are multiplexed with 16 data lines, and that will be available as AD15 to AD0. This is multiplexed address data bus. This is called as multiplexed address data bus. The reason for multiplexing these signals is we can reduce the number of pins. As the number of pins reduces, the area reduces, power reduces. Okay. So, even if you multiplex this address and data bus, the function of the microprocessor will not be affected. That is another condition. So, here this will be actually, if I split into 2 parts, this is A15 to A0, which is the lower order 16 bits of address, and D15 to D0, the entire data bus 16 bit data bus. So, when does this multiplexed bus will be used for carrying the address? When does this multiplexed address bus will be used to carry the data? So, normally in the first T cycle, if we take this the microprocessor operation, so here you have lower address bus. So, whatever I have discussed is already written here. So, when does this particular multiplexed address data bus will be used for carrying the address? Is during T1. So, T is actually T state, one clock period of any microprocessor is called as one T state. So, if I take the microprocessor cycle, it takes 4 T states, 8086 bus cycle, which is called as bus cycle. This will take 4 T states. I will show what are the T states. So, if I want to read or write the data So we require the address and data buses. As you have discussed it in the microprocessor operations, the first operation is microprocessor initiated operations, which are memory read, memory write, IO read, IO write. So for all these operations, what is required is the microprocessor requires address bus, data bus and some sort of control signals. So in that also there is a 3-step procedure to perform any of these 4 operations, which you have discussed in the earlier classes. So the first step is you have to identify the device with its address. Device can be memory or IO. So you have to identify the device with its address. So once if you identify the device with its address, then you generate the control signal, whether it's a read operation, write operation, you generate the control signal. Then third step is you transfer the data. So among these 3 steps, in the first step, identifying the device with its address, there only we require the address bus. So after that, generating the control signals, transfer of the data, so we don't need the address bus. That is why in the first T state, so this in the first T state, that is T1, AD 15 to AD naught is used to carry address information, because the first step in any microprocessor initiated operation is either memory read, memory write, IO read, IO write. So the very first step is you have to identify the device with its address. So we need address bus. So in the first T state, this will be used to carry the address. And similarly, we have the other totally 20-bit physical address is to be required. So these are the 16 bits. So remaining 4 bits are multiplexed with the status signals. So those are called as A19 / S6 to A16 / S3 is used to carry the address. So these are state, this is called actually the multiplexed, this is multiplexed address data bus, whereas this is multiplexed address status bus. So during the T1, so AD 15 to AD naught will carry address, that is A15 to A naught, and A19 / S6 to A16 / S3 carries A19 to A6 is total will get 20 address lines during the T1. Total 20 address lines will be available during the T1. So in T1, we will send the address, we will identify the device with its address. So the second step is you have to generate the control signals, then the next step is you have to transfer the data. So in subsequent T states, AD 15 to AD naught carry data, and A19 / S6 to A16 / S3 carry status signals. Because here we require the status signals and data bus for transferring of the data. Only in the first T states we require the address bus. So how this will be latched? So for that we are going to use another signal called address latch enable. Called ALE. So ALE is required to demultiplex address data bus as well as address status bus. These are multiplexed. To demultiplex this, we will use ALE. Use it to demultiplex address data bus, and address status bus. How exactly this will be demultiplexed? For that we require the latches. So we know what is meant by latch. Latch is some sort of D flip flop. D flip flop will act as a latch. Clocked D flip flop. So what is the operation of the D flip flop? So if this is negative edge triggered or positive edge triggered, if I assume that this is negative edge, this bubble represents negative edge triggered. This is clock. This is D. This is Q and Q bar. So if it is negative edge triggered flip flop, during the clock, as I have discussed it in the last class also, there are total 4 portions of the clock. This is ideal clock. So there is one positive edge, positive level, negative edge, negative level. So this particular flip flop will be enabled during negative style edge. So if I apply the clock signal at the negative edge, what happens? This flip flop will be enabled and whatever the data will be transferred to the output. Q becomes simply D. Whatever the data here will be transferred to the output at the negative edge of the clock signal. So simply output is equal to input. This is called latching of the input information. So the only condition for latching this data onto the output is the clock has to be changed from 1 to 0, which is negative edge. So if I use 8 such latches inside a IC, which is called octal latch. There are some ICs available which will act as octal latch, which is 8282. There is one IC. (8282) will act as octal latch. As the name implies octal, inside this there are say 8 D flip flops which will act as latches. So I am not showing the 8, so they will be having different 8 signals. So I will show these 8 signals with this symbol. This represents this is multiple lines, and this will be having clock which is common to all the flip flops. So this is clock is common to all the 8 flip flops. So we can use multiple latches. Here I am not showing this one. So total in 8086 total there are 20 lines has to be demultiplexed. Total 20 lines are multiplexed in 8086, out of which 16 are address lines multiplexed with data and 4 address lines are multiplexed with status. This is AD15 to AD0. So total 16 means, so I am not showing this one. There are 8282 chips here. So I am showing only single one only. So here I will show this as 16 lines. Means this each line AD0 will be connected to D input of one latch. AD1 will be connected to D input of the second latch. So like that there are 16 latches, means if I use two sets of 8282. So there are 16 D flip flops. So 16 AD0 to AD15 will be connected to the D inputs of all the latches. Similarly, so if I use one more 8282, so which will be having 8 latches, out of which I will use 4 lines which are A19/A6 to A16/S3. So totally there are 20 lines, means inside this you should have 20 D flip flops. So each 8282 will be having 8 D flip flops. So we need 3 such 8282s. I am not showing individually here, single 8282 only I am showing, but in fact here we require 3 number of 8282s. So the clock is common to all the 3 8282s and all the D flip flops inside that, but the inputs of D flip flops will be different. So So, there are totally 20 different signals are there from 8086. So, one signal we have to connect to the one input of each D flip flop, that is the configuration here. Then this clock will be applied to a signal called address latch enable. So, during the first clock cycle what happens is, I will place here address lines A15 to A0 and here status address lines A19 to A6. So, that time I will make this signal ALE signal as a low to high signal. This is actually practical clock, and this is ALE signal. So, during this portion of the ALE signal, this is called negative edge. So, at this portion this 8282s will be all enabled, thereby whatever the input data will be transferred. That time what happens is, this will be happen in the T1 state, this will happen in the T1 state. So, that time this multiplexed buses carries the address information. So, thereby the output will becomes only, this will be only A15 to A0 and this will be A16 to A19. So, this total 20 bits of the address bus is latched onto the output. So, this output will be there, this 20 address binds until the next clock cycle where the address latch enable goes from high to low. So, till this point, from this point to this point, so whatever the information that is latched will be available at the output of 8282. Now what happens is, because already I have latched this one, in subsequent clock cycles I can use this to carry only the status, I can use this to the carry only the data. This is data line D15 to D0, this is status lines S6 to S3. This is you can demultiplex. Now, address bus is available separately, data bus is available separately, status signals are available separately. So, this will be the operation to demultiplex the address data bus and then address status bus. So, for that we will use ALE signal. So, this is how we can demultiplex the address and data bus. So, these are the common signals, but ALE is signal which is available for minimum modes configuration. But here because this function is required, so I have discussed this ALE here itself. So, what are the other common signals? So, out of this I have discussed about the ground, AD15, all these up to AD0. Then if I go in this order, NMI, INTR, this already I have discussed in the last class, NMI and INTR. These are two interrupts of the 8086. I have already explained, NMI is non-maskable interrupt and this will be a positive edge triggered, INTR is a positive level triggered, and but INTR is maskable. So, this actually I have explained already while discussing about the microprocessor operations. Now, coming for the other signals, clock. So, we know that the microprocessor requires 5 megahertz clock. In case of a simple 8086, there are two versions. The other versions requires 8 megahertz and 10 megahertz. This clock has to be generated using the external crystal generator. There are different ways to generate the clock signal. So, oscillators, basically we have Colpitts oscillator, Hartley oscillator, but normally for the microprocessor to generate the clock signal for the microprocessor, we will use the crystal oscillator because of the stability. Crystal oscillators are more stable. So, that is why by using external crystal oscillator we will generate the clock frequency of 8086. Which will be for standard 8086 5 megahertz, and for the different versions we have 8 megahertz and 10 megahertz. So, this is nothing to do, externally you have to generate a clock signal using clock crystal oscillator. And ground we have already discussed VCT. So, AD16, AD15 is part of AD, this one. So, then coming for this status signals, we have discussed about the address data bus. Coming for the status signals, we have status signals here S3, S4, S5, S6. So, what is the function of this S3 to S6? The status signals S3 to S6. They are multiplexed with address lines. So, the function of S3, S2, S4, S3 will be operation so if they are 0 0, then this is extra segment. To access the extra segment, these two status signals should be 0 0. 0 1, this is for stack segment, and this is 1 0 code segment or no segment. And 1 1 is for data segment. This is the purpose of these two status signals S4 and S3. I am coming for S6. S6 is a status signal. So, during the hold operation, so this also I have explained in the microprocessor operations. So, hold will be the operation which will be used in direct memory access applications. As I have told, if I take the microprocessor and memory, IO, the normal way of data transfer is, so whatever the data if I want to transfer from memory to IO, so memory first it will transfer to the microprocessor will transfer to the IO. This is the normal conventional data transfer scheme. Whereas this is time consuming, so for that we can use a direct memory access through between this memory and IO. This is called DMA, direct memory access. But in order to perform this DMA operation, the microprocessor requires the control of the buses, microprocessor buses. For that, the microprocessor memory will request through hold signal is requesting for the buses of microprocessor, and hold acknowledge HLDA, the microprocessor will acknowledge and it will transfer the control to the microprocessor memory. So, during this signal S6 will be normally low, S6 is normally low, means logic 0. Whenever the microprocessor 8086 uses the buses. So, microprocessor can use the buses for performing its own operations. So, if the memory request for this buses through the hold signal, so whenever the microprocessor is performing using this buses, then S6 signal will be low. So, the memory will check the S6 signal and it will understand that microprocessor is using the buses. So, whenever the purpose of this buses is over, the use of the buses is over, then what happens is, so the microprocessor is ready to give the buses to the memory. So, in that case S6 become high, or in fact this is not high, it will go into the high impedance state. So, once this microprocessor uses the buses and the microprocessor is ready to give the buses to the memory, then it makes X6 as high impedance state. So, what is meant by high impedance state is, so in digital terminology we know logic 0 and logic 1. If I take a tri-state buffer, so buffer is basically current amplifier, but voltage will be same, input and output voltage will be same. So, if I take 0, if I apply 0 here, output is also 0, if I apply 1 here, output is also 1. There are two states, logic 0, logic 1. This is called two-state buffer. If I want tri-state, you have to incorporate one more control signal C here. This is tri-state. So, if C is equal to 1, normal operation. that if input is 0, output is also 0, if input is 1, output is 1. So, if C is equal to 0, then the buffer will enter into tri-state. Tri-state in the sense is also called as high impedance state. Also called as Z. High impedance means here the impedance will be high. If I take the high impedance, what happens? This almost will act as a open circuit. Means it will not draw the current from the device which is connected to this output. So, if it is not high impedance state, even if it is logic 0 also, it will draw some current from the gate which is connected to the output of this buffer. If it is high impedance state, almost this is open circuit, it will not draw any current, it will not load the device which is connected to the output of this buffer. That is meant by high impedance state. High impedance means almost is open circuit, it will not draw any current. So, it is not going to load the device which is connected to the output of the buffer, that is meant by high impedance state. So, here also what happens is, so after the microprocessor uses these buses, during the use, whenever the microprocessor uses the bus, S6 is low. After the use of the buses is over, 8086 is ready to give the buses to the peripheral device. That time what it makes is S6 will become high impedance state, then the control will be given to the memory. That is the status bus S6. And then next is there is one more status signal which is called S7 or by bus high enable. I will come to that later. So, now coming for this, the other signals such as DEN bar DT by R bar. So, before going for this function of the other pins, so I would like to explain about the bus cycles of 8086. As you already discussed the bus cycle, it will take 4 T states, T1, T2, T3, T4. But there is one wait state. So, if the external device is not ready, as we have discussed it in the last class also, so whenever this microprocessor is want to read the data from the peripheral, we know that the peripheral is slower when compared with the microprocessor. If the peripheral device is not ready, so what the microprocessor will do is it will enter into the wait state until the data is ready. So, but basically if this external peripheral device is ready, then it will take only 4 T states. As I have discussed it, to demultiplex address and data buses, status and address buses, ALE will goes high in the T state. So, during this point the address bus and data bus will be demultiplexed, address bus and status bus will be demultiplexed, as you have discussed just now. Similarly, there are 2 more signals called bus high enable and S7 signal, S7 to S3. So, as I have told, so like the status signals A19 to S6, A16 by S3, they are multiplexed. Similarly, there is one more status signal S7 which is multiplexed with bus high enable signal. I will come to the function of this bus high enable. So, this is multiplexed with S7. So, this multiplexed bus carries the address during the first clock cycle. You see here in the first clock cycle A19 to A16. Similarly, this bus high enable will be this BHE bar by S7 is also multiplexed signal. So, this will carry BHE bar information during T1 and in subsequent clock cycles S7. Here also in subsequent clock cycle S6 to S3 which we have already discussed. This is S7 to S3 including S3 to S6 and then S7. So, in subsequent clock cycles. So, here this address bus will be latched as you have already discussed. So, there are 2 more signals called read bar, DEN bar, DT by R bar. So, in order to read the data from the external devices, so the microprocessor can read the data from external device such as transceiver. There is one device called 8286 which is called transceiver. Transceiver is the combination of transmitter and receiver. Plus receiver. So in the transmitter you have taken trans, in the receiver you have taken ceiver, so it is called transceiver. Transceiver is combination of transmitter and receiver. So using this transceiver, this 8286 will act as a transceiver. So the microprocessor can read the data from 8286 or microprocessor can write the data into 8286. So for that it uses read bar signal, and then there are two extra signals which are called DEN bar, DT bar. DEN bar and then DT bar, DT by R bar. So in order to perform any operation, whether it is a read operation or write operation, this is read operation. So DEN bar should be low, but this goes, the difference between the read and write is, in case of read operation DEN bar goes low, so during this T2 cycle it will be low up to T4 cycle. So whereas in case of write operation, so this DEN bar is low during T2, whereas here is just earlier than this one. So why? Because in the read operation what happens is, the peripheral device is low device, so the microprocessor has to wait, it cannot directly read. In case of write, means microprocessor is writing something to sending some data to the transceiver. So because already microprocessor is a fast device, so it will send immediately. That is why this DEN bar will be low in case of write operation, early when compared with DEN bar of read operation. I think you understand the difference between DEN bar in read cycle and write cycle. In case of read cycle, the microprocessor has to read the data from the external device which is slower one, so the operation will be a little bit delayed. So whereas in case of write operation, the microprocessor will send the data to the transceiver. So because microprocessor is already fast device, so this DEN bar will be low a bit earlier than that of in read cycle. Similarly in case of write bar will be there. This, all these operations are common, ALE, this entire thing. The only difference between the read and write cycles is, so here in place of write bar there read bar will be there. DEN bar will be goes low earlier when compared with the DEN bar of read cycle, because the microprocessor is fast device. And DT by R bar is, so in case of write cycle, DT by R bar will be, DT by R bar represents data transmit slash receive bar. As the name implies, if this is one, implies data transmit from microprocessor, which is write operation. So in case of write operation, this DT by R bar should be high, whereas in case of read operation it has to receive, microprocessor has to receive. So DT by R bar should be low, implies data is taken from peripheral. So that means it is a read operation. That is why in case of read operation we can see that DT by R bar is low. In case of write operation, DT by R bar is high. And then DN bar, here you have write bar signal, whereas in this case we have read bar signal. Another difference is DN bar will be goes low in both the cases because data enable. DN bar is stands for data enable. Stands for data enable. D for data, En for enable. So in any case, whether you want to perform the read operation or write operation, data enable should be 0. But only difference is, in case of read operation, because of the peripheral device is slow, then DN bar goes to low, a bit delayed when compared with the DN bar of write cycle. That is the only difference in DN, but both are lows. Here read bar will be there, DT by R bar will be low. So in case of write cycle, DT by R bar is high, this is write bar signal, whereas DN bar goes to low a bit earlier than that of read cycle. This is about the functions of dt by r bar, den bar, read bar, write bar. So for write operation, for read operation what happens is, for read operation read bar should be 0. For write operation wr bar will be 0. So this will complete the functions of dt by r bar, den bar, read bar and write bar, 4 signals of the microprocessor. Then S7 and BHE bar. So this is bus high enable, which is going to enable the higher order bus of this signal. So now coming for the function of BHE bar and S7. BHE bar, as the name implies, bus high enable. The full form of this one is bus high enable. So which enables the higher order 8 bits of the bus. So what are the higher order 8 bits of the data bus? Is D15 to D8. Lower order is D7 to D0. Okay. How this will be enabled? So for that we have to discuss about the memory bank concept of 8086. So we know that in 8086 the memory will be divided into banks. Memory of 8086 is, maximum memory capacity is 2 raised to the power of 20, because 20 address lines are there. Relation between the maximum memory that can be connected to 8086 or any microprocessor and the number of address lines is 2 raised to the power of number of address lines is the maximum memory capacity. This is nothing but 1 megabyte. So in fact this is in terms of the kilobytes. If you want to write this, as I have told already, 1 kilo is not equal to 1000. In microprocessor terminology, 1 kilobyte means it is 1024 bytes. So this can be written as 1 kilo into 1 kilo, 1 kilobyte into 1 kilobyte. If I substitute this 1 kilobyte, this is 1024 kilobytes. 1 megabyte is equal to 1024 kilobytes. So what is the half of this one? Is 512 kilobytes. Half of this is 512 kilobytes. So the total 1 megabyte, which is 1024 kilobytes of the memory, will be divided into, if I take this total 1 megabyte of the memory, so we have 20 bit address line. The starting and ending address of this one will be, this will be FF, FH, and this will be 0000H. So this is total 1 megabyte memory, which is 1024 kilobytes. In 8086 what happens is, so now to enable a 16-bit data from the memory, because each location is capable of storing only 8 bits of the information. This will contain 8 bits of the information. The meaning of 1024 or 1 megabyte is, we have 1024 into 1024 locations, and each location is capable of storing 8 bits of the information. But 8086 is a 16-bit microprocessor. In some applications we need 16-bit data also. So which we cannot read, for that we require the 2 clock cycles. At a time you can read only the 8 bits of the data. So to read the 16 bit of the data we require 2 clock cycles. So instead of that, if you want to parallelly read the total 16 bits simultaneously, so the memory is divided into 2 banks, which is called odd bank and even bank. Now what is the capacity of each bank? Is 512 kilobytes. So this is 512 kilobytes, this is 512 kilobytes. The address of this one will be This is odd addressed, this is even addressed. So what are the addresses? Total addresses are 000. So 00000H. This is the starting address of the total 512 kilobytes of the memory that will goes to the even bank. The second location, which is 00001, will goes to the odd bank alternatively, and then the next one will be here 00002H, and here this will be 00003H. This will be 00004H, 00005H, and so on. And what about the last address, FFFFFH? This is odd address. So odd address will be here, because starting with here it has to end with this. Okay. So this is odd address 15. So FFFFH will be the odd address. The one address which is before this one is FFFFEH, and the one which is before this one is FFFFDH, and this one will be FFFFCH. This one will be FFFFBH, and this one will be FFFFAH, and so on. So this will be contains only the contents of the even addressed locations. This will contain odd addressed locations. So what is the capacity of this? This is 512 kilobytes, and here also this is another 512 kilobytes. So each memory signal will be having some chip enabled signals. In order to select this particular chip at all, so we require some chip select signal. After selecting the chip as a whole, we will select the particular location. That is how the memory read or write operation has to be performed. To perform either read operation or write operation, there will be some chip select signal corresponding to each memory. Normally these are active low signals. This is called chip select signal, CS bar. So in order to select any location, the first requirement is you have to select the chip. If I apply a logic 0 on this particular chip select signal, that particular chip is selected. After that you select the location. So here this higher order bus will be supplied by this one. This will give total 8 bits, this will give total 8 bits. Totally we have 16-bit data bus. So this will give this total 8 bits of the data. This will give another 8 bit of the data. This will give D15 to D8, D7 to D0. Overall this will be D0 to D15, 16 bits. So in between this one, this is higher order data bus. So this will be connected to bus high enable signal, BHE bar. As the name implies, bus high enable signal. So this will be connected to the even addressed bank. And this will be connected to, so in order to select this for only the odd address, so we can simply give A0. Because so we know that total 20 address lines are there, A19, A18, A17, so on up to A2, A1, A0. For all addresses, even address, say if I take the starting address, all zeros, the next address is all zeros, last one is 1, the next address is zeros, then this is 2, and so on. So for even addresses, A0 is 0, for odd addresses A0 is 1. Okay. So when does this will be selected? So A0 is equal to 0 for even address. A0 is 0 for even address. So for A0 is 0 even address, this will select. So this should be even address line. This is even address, and this should be odd address. Understand? So this is odd address because this is even address because A0 is connected. A0 is 0 for only even address lanes. So for even address lane A0 is 0, so chip select is 0, this chip will be selected. Whereas higher order bus is odd address, so BHE bar will be used for selecting this chip select. Now we can form the table BHE bar versus A0. And what is the type of memory operation? If both are zeros, what happens? This is also 0, this chip select bar is 0, means this chip will be selected, this chip also will be selected, this will give 8-bit information, this will give 8-bit information. At a time we can read 2 bytes, which is called one word. This is 2-byte operation. 2 byte is normally called as word. This is word operation because both the banks will be enabled. Because A0 is connected to chip select of even bank, BHE bar is connected to chip select of odd bank. So because both are 0, both the banks will be selected. One bank will give 8 bit, another bank will give 8 bit. Overall it will be 2 byte or it will be one word. Now 0, 1, so only 1 byte from which bank is selected? From, so this BHE bar is higher order, which is odd, from odd bank. 1 0, 1 byte from even bank. Both are ones, none of the chips will be selected, so no data. Entire data bus will not be enabled. So you see here BHE bar is 0, only the odd bank will give one data which is higher order bits, this will give lower order bits. So this, if bus enable bar is 0, this will be 1 byte from the odd bank, which will be higher order 8 bits, D15 to D8, and in this case D7 to D0. In this case the entire thing D15 to D0. Here no bus will be selected. This is the purpose of BHE bar and A0. Coming for one more status signal, which is called S7. There is one more status signal, but this is not multiplexed with any other signal. So this normally this will be low during interrupt acknowledged signal. Interrupt acknowledge. So whenever the microprocessor is executing some program, as we have discussed in the last class, so any external device can interrupt and it can ask the microprocessor to execute some emergency task. So during that time it will request the microprocessor through INTR or NMI. Okay. So whenever the microprocessor receives the signal, interrupt signal, it completes the execution of the current instruction. Then it will send the interrupt acknowledge signal. There is one more signal called INTA bar, which is called interrupt acknowledge signal. So whenever the microprocessor puts a logic 0 on this is active low signal, that means the external device understands that the microprocessor is going to service the interrupt routine of that particular interrupt. Okay. So during this time interrupt acknowledge cycle, this S7 will be kept low, otherwise it can be tri-stated, so that it will not carry, it will not draw any current, it will not overload the device which is connected to the S7 pin. So these are the different pins. So now what are the pins that are left? So here we have discussed about these pins, S3 to S6, BHE bar by S7. Then there is one pin called MN by MX, MN by MX bar. This, as I have told, there are two modes, minimum mode and maximum mode. MN stands for minimum, MX stands for maximum. So if this is equal to 1, implies minimum mode, single user. To operate the 8086 in minimum mode, you have to set this pin to 1. If you set this pin to 0, the microprocessor operates in maximum mode, which is multiprocessor mode. So, till now we have discussed about the all common signals, and there are some signals used in minimum mode. So, we have discussed about all the common signals here and all the common signals here up to this point. So, I will come to this later. Then the remaining 3 common signals are test bar, ready and reset. So, the other signals are the common signals test bar, so test bar signal, coming for the test bar signal. So, there is one instruction called wait instruction. I will discuss this while discussing about the instruction set. So, whenever the microprocessor executes this instruction, as the name implies, microprocessor simply it will wait. Okay. So, till which time it will be wait? So, this microprocessor will wait until test bar is equal to 0. So, as long as test bar is equal to 1, it will wait only. So, once if test bar is 0, it will stop waiting, it will come out of the wait cycle and it will perform the various tasks. That is a simple purpose of test signal. And ready and reset signal we have already discussed. Ready signal. So, this will be used by the external device. So, whenever this ready signal is 1, the microprocessor reads the data from the device, otherwise simply it will enter into the wait state. This I have already discussed while discussing about the externally initiated operations. Similarly, reset. Whenever the microprocessor is reset, then the microprocessor will suspend all the operations, internal operations, this also I already discussed. It will make stack segment, data segment, extra segment, instruction pointer flags to 0, then code segment is FFFFH. So, whenever this reset is removed, the next instruction that is to be fetched will be FFFF0H, which we have already discussed in the last class. So, this is all about the common signals and some minimum mode signals. So, the functions of this maximum mode signal and remaining minimum mode signals we will discuss in the next class. Thank you.